Okay, so we're gonna begin a new chapter. Now, remember, all we have been doing so far is what we call integral calculus, okay? So now we're going to enter the second part, if you will, of calculus, which is called, sorry, we have been doing differential calculus. Now we're gonna enter the second part, which is called integral calculus. And, okay, I'm gonna write what I'm gonna write, but just to give you visual information. You know, the main question that we were trying to answer with the differential calculus is, we were trying to make sense of something like this. You have your function, pick a point. We wanted to make sense of what this is, right? The tangent line of the function at a point, and then we know that we already have a point, we need to make sense of the slope of this function, of this line, and that's where the notion of derivative comes. And then, as you know, just using the idea of derivative has a lot of implication, that you can tell everything about a function by looking at the information about the derivative, the second derivative, and all of that. That you can sketch a function. So that's differential calculus and the applications of optimization, etc., etc. Now there is another side of the story, which is what we call integral calculus, and the birthplace of it is the following. Again, you have your function f, but this time I don't want to talk about tangent lines. What I want to talk is about something else. Pick an interval from a to b. You have your function. No, there is a region under the graph of the function. Between the graph of the function and the x-axis, there is a region in the plane. A natural question to ask is, okay, what is the area of this guy? Okay, what's the area of this region? This is what we want to explore right now. Now, what we're gonna do today, we're not going to get to the area question. We're gonna be playing like a little game in which we know derivative. Now we're gonna reverse this. It turns out that when we ask this question about area, there is a theorem called fundamental theorem of calculus that actually these two things seems to be completely unrelated, but they are actually linked to each other by the fundamental theorem of calculus. That tells you that if you want to compute area, you can play this game about reversing derivative to be able to understand the area under the graph of a function. In calculus 2, you're going to continue studying these notions, and then you're going to see that this notion of area actually is more general, and you can use it to calculate volumes, surface area, a bunch of other stuff. Okay? But we're going to do the basics here. Okay, so we did one part of calculus, which is differential calculus, and now we're gonna begin the new one, which is integral calculus. Again, we're only going to scratch the surface, so there's no reason why you shouldn't do good on this exam. Just because we're gonna talk about basic stuff, okay? It's just definitions, and then not gonna be complicated integral for you to solve and so on. Now, the secret for this is practice. Practice, practice, practice. You just need to sit down the problem. It's just like factoring. If I explain factoring to you and you never do a factoring problem, and then I give you a problem, you're going to take half an hour to do a factoring problem. Now, if you do 20 factoring problems, somebody walking on the street gives you a polynomial, and then probably you can factor it just walking, a second degree polynomial. Because you have practiced this. But if you don't practice, it's going to take you forever to do something. Okay? So keep that in mind. You just need to do problems. Because ideas are not really that complicated. Anyways, again, of course, all of this is relative, right? We say that something is not complicated, but hopefully you will get the hang of this. All right, let's see. So let's start with a little example. First, let's understand what is this idea of antiderivative. Okay, that's why I wanted you to see the video, so you will have already some sort of preconceived idea when you come here, so it will be easy to understand. So let's do this little example. So find a function whose derivative is 3x squared. Just using the knowledge that you have, what function can you think about so that when you take the derivative, you get 3x squared? X cubed, right? So for example, we can, this function f, we can say is a function x cubed. Yes? Since when we take the derivative of f, we get 3x squared. Everybody okay with this? And notice that this is little function f. Okay, this little thing that we just did, and there is a name for this, we call this function, capital F, an antiderivative of the function 3x squared, of little f. Okay? So, this is called an antiderivative of the little function f. So, what's the definition of an antiderivative? An antiderivative of a function is another function. So when you take the derivative, it gives you the function that you started with. Do you understand this? Okay. So let's define this. So a function f is an antiderivative of little f on an interval I when the derivative of capital F equals little f for all x in I. Okay, that's all it is. So I give you a function, and the game that we're going to be playing is I want you to give me another function whose derivative is the one that I gave. That's what the type of game that we're going to play. Now, of course, depending how complex this little function f is, you know, it may be a little bit more complex for you to figure out what capital F is, and that's why there are several techniques to streamline this process. Okay, and roughly, I would say from one third to a half of calculus 2 will be devoted to learning more advanced techniques of figuring out this capital F when this little f is really complicated. Okay, here we're just gonna scratch the surface, but Cal 2 will continue with this idea. Okay, so for example, now let's understand that there are some subtleties to this question. For example, your classmate told me x cubed. How about another one? Can you give me another antiderivative?
X cubed plus c, or a constant.
So give me another antiderivative.
X cubed plus 1.
Okay, x cubed plus 1, x cubed plus 2, x cubed plus 20. There are actually infinitely many answers to this question. Do you understand this? The moment that you find one antiderivative, you already have a whole family of antiderivatives. Just do plus c, because the derivative of a constant is 0. Okay?
Also,
so let me.
In the homework, I saw this where it was like the three next to separate and add together with a denominator on the bottom, like a fraction, and 3 over x to the second power, but add 1 on the bottom, 3.
We're going to get to that. We're going to get to that. So, referring to the above example, find another antiderivative. For example, we could say, all right, we can consider the function g of x, which is, I don't know, x cubed plus 1, right? Or any other. So, in fact, we can just look at y equals x cubed plus c, where c is any constant, so this is an antiderivative of f of x equals 3x squared. And the whole point is because the derivative of a constant is 0. Does everybody understand this? Now, here is a non-trivial question. Are there others? So, we know that, okay, x cubed is an antiderivative of 3x squared. We know that x cubed plus any constant is an antiderivative of 3x squared. But how about other functions? Could there be a weird function with radicals, I don't know, all the stuff going on, so that eventually after you take derivative and simplify everything, you end up getting 3x squared? Or are all the antiderivatives this simple for this function? Do they all look like x cubed plus something? In other words, a vertical translation of the x cubed function. So this is the next question, because you know our job now is, what we want to do is, when I ask you give me an antiderivative, I really want to know all the antiderivatives. Okay, so we really want to figure out all the antiderivatives of a fixed function. We know there are infinitely many. Here are infinitely many already. Now, are there others that do not belong to this family? And maybe they are complicated enough so when you take derivative, things simplify, whatever, and then product rule this and that, and then eventually end up getting 3x squared. Is it possible to have something like that? So let's try to answer this question. The good thing is that no. Here is the non-trivial answer to this. Is that actually the moment that you find one antiderivative, that's it. Any other antiderivative has to have the form that guy plus c, where c is a constant. Okay? So 3x squared doesn't have any other antiderivative unless they look like x cubed plus c. So that's a theorem, and we can actually prove it. We have the knowledge to prove this, so let's justify this. So if f is an antiderivative, of little f on an interval I, then g is an antiderivative of f on I if and only if g is of the form g of x equals capital F plus c for all x in I where c is a constant. So what this is basically telling us is that if you want to find all antiderivative of a function, all you need to do is figure out one, whatever way you can, and then you just do plus c, and you're going to have everybody in there. Okay? You're not going to be missing any other. So let's actually prove this. Because the proof is nice and simple. So first of all, this is an if and only if statement. So it's a two-sided statement. So it means if the left side is true, then the right-hand side must be true, and also the other way around. If the right side is true, then the left-hand side must be true. So there is one direction here that is super obvious. For example, if G equals f of x plus c, capital F plus c, then G is an antiderivative. So let's prove this statement first. So assume that G of x has this form. Do you see that if G of x equals this, then this must be an antiderivative of little f? How would you justify this? Just take derivative, right? So then what happens when we do G prime? What is G prime equal to? That would be capital F prime plus 0. But what is capital F prime? By definition, capital F is an antiderivative of little f, so this equals little f. Okay? So, of course, if you already have an antiderivative, if you do plus c, you're going to get another antiderivative. So that's this direction, so that's pretty straightforward. The non-trivial question is the other one, that any G has to have this form. Okay? So, let's argue this. And now assume that that G is another antiderivative of little f. Remember, we already have one, which is capital F. That's the initial hypothesis of the theorem. So assume that we have another one. Our job is to show that this G must be of this form. Okay? That it has no other choice than to look like that. Okay. Let's see. What can we say from here? What does it mean for G to be an antiderivative of little f? What does that mean?
G prime is that.
Very good. You know, that's the definition. That means if I take the derivative, I'm going to get little f. Everybody okay with this? All right. Now, here is the trick, or I guess the clever idea to argue this theorem, is that now we're going to introduce a new function. So consider the following function. So consider the function h of x. I'm going to call it h, and it's going to be actually the difference between f and g. So let's see. I'm going to write it as g of x minus f of x. Okay. Nobody can stop me from writing this down. I have two functions. I have my capital F. I have my capital G. I can look at their difference. This is a new function. Everybody agree with this? Now, what can we say about this function? Let's see. What happens if I take derivative? What's the derivative of h?
Should be 0.
So let's see. This is g prime minus f prime, right? Derivative of a difference is the difference of the derivative. What is g prime?
0.
What is g prime? F of x, because g is an antiderivative, right? And what is f prime? Is also little f. So this is going to be equal to 0. And this is true for all x in I. Yes? So h is a function whose derivative is 0 for all x in the interval I. What does that mean about the function h? If you have a function whose derivative is completely 0 on an entire interval, what does that mean about the function on that interval? Think about it again. What does positive derivative means? What does it mean positive derivative? It's increasing. What does it mean to have negative derivative? So what does it mean to have derivative 0? It's a constant. The function has to be flat. It has no slope on that interval, right? So this h has to be a constant. So h of x is actually equal to a constant. Let's call it c on the entire interval I. So going back to what we have then that g minus f, which is equal to h, is actually a constant. Solving for g, then we see that g is actually f of x plus c. Okay? So bottom line, now we just argue here that any function that's an antiderivative has to have this form. Okay? So now you know that when you told me an antiderivative of 3x squared, you told me x cubed, any other answer that you could have given me had to be x cubed plus something. There is no other choice. There is no weird function So when you take the derivative and simplify, you're going to get 3x squared. They have to belong here. They have to be in this family. Okay? So that means that if you want to find all antiderivative of a function, what do? Here's a recipe. You just need to find one, and then you do plus c. So that plus c is important because you want to know all the antiderivatives. Okay? And this theorem tells you that all of them, they have this form. You just need to fight for this one. Okay? So what we're going to do now is we're going to learn how to figure out one antiderivative. Because then we just do plus c to get all the rest. Does that make sense? Okay. So hopefully you notice how we are using knowledge from before to get these statements. Okay? All right. So here's a summary. So this was the end of the proof here. So to find all antiderivative of a function, what we do is we find one antiderivative. We find one antiderivative and then add an arbitrary constant. Okay? That's all we have to do. So that C, we call it an arbitrary constant because it can be whatever you want. Okay? It's a constant. Whatever is your favorite number, you can think about it that way. All right, so let's see. Let's do an example. So that's why sometimes we refer to it as the family of all antiderivatives. Okay? Because it's a family. Why a family? For example, in the case of the x cubed, this is just the x cubed function with, vertical translations up or down, depending whether the constant is positive or negative. So we call this a family of functions because they all look the same. They are just translated vertically, up or down. All right, so let's see. Let's find the family of all antiderivatives of the function 7x. So what do we need to do to answer this question? We just need to find one antiderivative, and then we will know exactly what the answer will be, right? So we just need one antiderivative. What is it? So think about a function whose derivative would be 7x.
X to the 7th power.
What is it? Well, when you take derivative, that's 7x to the 6. So it doesn't work.
Is this 7 over 2 times x to the 2nd power?
So what do you think? I mean, you can verify your answer.
Yeah.
I think so. You take out
The derivative, and what do you get? You get 7x. So good. So one antiderivative is 7x squared over 2. Or if you want, 7 half x squared. Again, right now you're just using your sheer knowledge from before, right? Just trying to undo whatever you can, right? For example, here what you can use is the fact that, okay, we have I'm going to write that down later. We have a property on the derivative level that says that you can take constants out of the derivative, right? Now, when you're doing this process, that means that you can kind of ignore the constant for a second and focus on the variable part. So find an antiderivative of x. What would be an antiderivative of x? X squared over 2. Then that times 7 will be an antiderivative of this guy, which indeed, that's what happened, right? X squared over 2 times 7. So we're going to see those formal procedures later on. Okay, so we found one antiderivative. So what are all the antiderivatives of this function?
7 over 2 times x squared plus c.
Plus c, where c is an arbitrary constant. Now you know any other antiderivative that anybody from whatever country or whatever work, as long as they work with the same definition, come in and tell you they have to be 7 over 2x squared plus a number. They cannot tell you something else because we just proved it. Okay? So all antiderivatives of little f are e of x equals 7 over 2x squared plus c, where c is an arbitrary constant. Are you okay with this? Okay, now we have a notation for this. Okay, so we have a notation to ask you, for example, normally I will tell you in words, find the derivative of. What notation do we have for something like that? We write ddx of a function, and then I'm basically asking you find the derivative of this function, right? Well, similarly, we have a notation for this statement, find all antiderivative of the following function. There's a way to write this down, okay? So the way that we write that is we use a sign, a symbol that we call an integral symbol. It's called an integral. And let me say this. So we write this as follows. So this is now a notation, okay? So we're gonna use, so we use the integral symbol, so we use the symbol, so it looks like this, it's like a short and big S, okay? Now, this is a package, okay? So I'm gonna put a line here just to indicate that this is a blank. This is where you will put your function, okay? So this symbol comes together with this, okay? Dx, because x is the variable. If the variable would have been t, then you put dt, and so on, okay? This is a package. This guy and this guy, they come together. They are not separated, okay? This has a meaning on its own, but you studied that, for example, in Cat 3, you talk about differentials, and then this is called differential, etc. And it kind of satisfies similar properties than derivative, okay? You can think of this as something very tiny, very small, an infinitesimal quantity. But you don't have to worry about that right now. This is just a package. Every time that you write this guy, I need to see this. If I don't see this, I don't know what you're writing. Do you understand what I'm saying? These two things, this is a package. So we are going to use this symbol to indicate the family of all antiderivative. Now, of course, you want to know the family of all antiderivative of what? So what we write here is a function. Okay, here you're going to write your function. Now I don't need a line. Okay, so we write this, and then that means the family of all antiderivative of little f. Okay, so what we have done is that, and we call this an indefinite integer. On Friday, I will explain to you what is a definite integral. A definite integral is what is involved in the computation of area and all of this business. Okay, but right now this has nothing to do with area so far. Okay, we're just playing a game of going back the rules that we know from derivatives. That's how we're doing. The surprising thing is that this little game helps you to compute area, believe it or not, which is actually very surprising. So anyways, we call this an indefinite integral. And so with this new notation now, what we have done is that we show that the integral, we don't say the indefinite integral of, we say integral of, but you could say indefinite integral. So the integral 7x, what is this equal to?
7x squared.
7 over 2x squared plus c, right? And again, this is just a compressed and nice way of writing the sentences that are written above. The family of all antiderivative of the function 7x is 7 over 2x squared plus c, where c is an arbitrary constant. That big sentence that I just said is summarized in this line. Do you understand? I'm going to be using this notation from now on because this is the notation that we use. Okay? But that's all I'm asking you. And you know that to answer the question, you just need to find one antiderivative and then do plus c. So c is sometimes referred to as the constant of integration. Okay? So we call this the constant of integration. And I guess another example is, what's the integral of 3x squared? X cubed plus c. Right? That's the one that was the first one that we computed today. All right, questions about this? Do you understand this? Okay, good. So now, let's see, before I go on, let me introduce another little example, which is the notion of a differential equation, okay? So a differential equation is just an equation that involves x, y, and derivatives of y. Okay, that's what a differential equation is. Most of you may need to, if you're doing engineering and so on, you may need to take differential equation. You do that after you do calculus 2. Why? Because you need to know integration to be able to solve differential equations. Okay, so after Cal 2, then there is a whole course for this, and you know there's a whole field of research in differential equation. I'm just going to define what the simplest type of differential equation is and give you an idea of how you solve those simplest type of differential equations, and that's it. Okay? Like I said, this is a whole course that you will start. All right? But the point is that you need integration to be able to deal with differential equations. So this question that we ask here can be asked in a different way, in the language of differential equations. Okay? So yet another way to express the same idea is via differential equations. In this case, we're talking about ordinary differential equation. So, definition. I'm doing this because in the homework you have a couple of problems in which instead of they asking you for an integral, they ask you the question via a differential equation. But they are actually asking you the same thing. And you will see it's actually more straightforward when you see it. So, a differential equation is an equation so I should say an ordinary, because when you have more than one variable, then you have partial differential equations, and that's a different story. So an ordinary differential equation is an equation. I'm going to give you a very rough definition, just so that when you look at it, you can identify it. An ordinary differential equation is an equation involving the variables. Let's say the independent variable is x, but it could be t, and then instead of x, you write t, etc. Okay? Involving the variables x, y, and derivatives of y. And then typically the order, now in differential equation, you will study this, but then there's a notion of an order to differential equation. Just like polynomials have degrees, right? Depending on what's the highest power and so on. The order of a differential equation has to do with the highest derivative that show up. Because you may have y prime, but you may have y double prime, y triple prime, etc. So a first order differential equation, you only see y prime showing up. The second order may have y prime and y double prime. And the techniques to solve them are different. Okay? Okay. So it's an equation involving the variables x, y, and derivative of y. So for example, I can ask you to solve the following differential equation. So solve the differential equation y prime, or let me be more specific, dy dx, or you can just write y prime, equals 7x. So this is a little equation, right? In this case, you see the derivative of y and you see x. There's no y, it's okay. It doesn't have to be there, okay? But it's just involving the variables that is here. This is an example of differential equation. But how do you solve this? This is just another way of asking you the same thing. What am I asking? What's the solution here? The solution here is a function y whose derivative is 7x. So what are the solutions here? All antiderivative of 7x. You understand this? So here, the point is that the solution here is a function y. So that when you take the derivative, you get 7x. So y is an antiderivative. So really all we are asking here is find all the possible antiderivatives the 7x has. So that will be all the solutions. Do you understand what I'm saying? So if you want to solve this, of course, we say, okay, I know what y is. Y is going to be a function of x, and it's going to be just a collection of all antiderivatives. So 7x. Remember, this is a way of saying all antiderivative of 7x. And we did this already. So that means the solution to this differential equation is 7 over 2 x squared plus c, where c is an arbitrary constant. So again, different language, but it's the same question. I'm asking you exactly the same thing, just from a different perspective. And for example, when you model behavior and situations in nature, this is what you counter. What you counter is differential equations, because what you see is quantities and how the quantities change. And remember, what's derivative? Rate of change with respect of time. When you're doing experiment, when you're measuring stuff, you see a particle moving, what is it that you can visually measure very quickly? How fast that particle is moving, like how fast it's changing from position A to position B. That's ds dt, where s would be the distance function, right? That's the velocity. So from the velocity, then you want to kind of deduce, okay, what would be the equation that describes the motion? And when you're measuring quantities, you can see, you do an experiment, and then you can measure the change in a certain quantity. So what you're really looking at is the rate of change, the derivative. And from that information, then you want to deduce what is the quantity itself. Population, you want to see how fast the population is growing. That's what you can see. Oh, from this year to this year, the population grew by this much. So you can, from some experiment, you can say, oh, the rate of change seems to be this. Then you solve that differential equation, and then you get the population growth function that you studied back in pre-calculus with exponentials and all of that business. Okay, so this is the language of nature, the differential equations. Okay, that's why it is important. You rarely are gonna come around and see functions themselves manifesting. You see how the quantities relate to each other. So you write a differential equation, of course, way more complicated than what I'm showing here. Okay, and then from that information, you want to deduce the functions that obey those relations. Okay. Okay, so that's this, and so that's a different language. Now let me just say something else. There is a notion of initial value problem. What is this? Right now, the solution here is infinitely many functions, right? But sometimes you want a specific one. Okay? So for example, let's think about it graphically. So graphically, what is this? This is the parabola. Let's say this is the parabola 7 over 2x squared. And then, you just have a bunch of translations of this, up and down, okay, and so on and so forth. So this is in general, this would be, y equals 7 over 2x squared plus c for some particular c. So let me call it plus c2. Let's say that this is c1, and, y equals 7 over 2x squared plus c1, and so on and so forth, okay? So the question is sometimes, let's say I want this one. I don't want anybody else, I want this one. So how can you say that? The first line here is telling you, okay, I want all antiderivatives, so this means the entire family. Now, how do you single out a particular one? You give a point that you want the function to satisfy. So for example, I want all antiderivative of 7x, but with the condition, so this is what's called an initial value problem. So I want all the antiderivative of 7x, but with the condition that, for example, when you plug in 0, you get 7. Let's say I want this. Okay? So that means that from all of these families, I want the one that the point 0,7 has to be on. Do you understand what I'm saying? So for example, it will be one from the ones here on top. Yes? So how do you figure this out? Well, pretty easy. Get all the families. This is called the general solution of the differential equation. And then you use the condition to figure out what this guy is. Okay? So this is called the general solution. And what we want is a particular solution, just one of them. Okay? The one that satisfies this. Okay, that's fine. So what's the solution? Okay, I know that y equals 7 over 2x squared plus c, right? We solved that from before, but now we use the initial condition. This is called the initial condition. If you have a second order differential equation, you need to be given two initial conditions. Okay? Either about y or either about y and y prime, right? But you have to be given two initial conditions. So this is the solution, and now what do we know? We know that when x is 0, y is 7. So y is 7 when x is 0. And from here it follows that c must be 7. So then this tells me that y of x equals 7 over 2x squared plus 7 is the solution. To the initial value problem. Do you understand this? Okay, this is called a particular solution.
Oh, that's the question I saw in the homework.
So there are questions like this. So that's why I'm telling you this so that you can understand, because it's just a matter of language, okay? Because, for example, if it's about integrals, then you may see that they may ask you, okay, find an antiderivative, but then they will tell you such that if you plug in 2, you get 3. That's equivalent to what I'm saying down there. What they want you to do is you do this, and then you figure out, with that condition, you figure out the constant that you need by plugging in your x and your y. Does that make sense? Okay. All right. Any questions? Again, I'm just describing a language here. Okay. Now we're gonna get into. Now the question is, okay, fine. How do we find all of these guys? How do we find antiderivative when the function comes our way? Let's start talking about techniques to do this. Are you okay? Right. Also, just another word. Remember, there's a problem like this in the homework. Velocity is what? Derivative of what? Of position, of the distance function. Acceleration is what? The second derivative of position or the first derivative of the velocity. Okay? So there will be questions about this, like they tell you the acceleration of an object, and from that they want you to, and they give you some initial conditions, and they want you to find the position function. For example, if a free fall object, you know, it has a constant acceleration due to gravity. Yes? So with that information, and with a couple of initial conditions, like maybe the initial height, and then maybe the initial velocity or something like that, then you can figure out the height function for the object. Okay? How? You take the integral, you find an antiderivative that's going to give you the velocity. You use an initial condition to find your constant, and then you integrate that again to get the position, and you use the other initial condition to find the constant. Do you understand what I'm saying? Okay. So in the homework, you will see these things, but just remember that. So I guess, let me say here, recall, so it's written here, that if x of t is the position function of a particle, then the velocity is dx dt, okay, is the velocity, and then the acceleration is dv dt, which is also the second derivative of the velocity of the position function. Okay? If we have time today, when we're done, then I'm probably going to go back to homework and pick up one of these examples and do it, so you see exactly what I'm saying. Okay? But just roughly speaking, if you have a free fall object, let's see, mind that you have, actually with this should be enough. This is the ground. You are here, right? And let's say that you have here an apple, whatever you want, okay? And then drops. So if you drop something, what does that mean? So let's say that this has an initial height of h0, okay? So that means h of 0 equals h0, okay? And what else do you know if you drop something? Okay, you know the acceleration, which is constant. What else do you know? I mean, the acceleration is always there. Why the word drop? What does dropping mean?
It's going down.
Drop means?
The height is negative.
Drops means let it go. Not this. This is throw. Drop something. What does dropping mean?
So you're saying the initial velocity is 0?
Very good. When you drop something, initial velocity is 0. So here you have another initial condition, v of 0 is equal to 0. Do you understand this? Yes? Okay, so with this information, let's get the height formula. So find h of t. Let's find a formula for this. Well, we know that acceleration due to gravity is a constant, right? In this case, it's going to be 9.8 meters per second. Typically, we use meters per second squared. If you use feet per second, I think it's 32. Is it? I think it's 32 feet per second. Anyways, I'm going to use meters per second squared. So the acceleration is due to gravity. So we call it g, but I'm just going to write a is 9.8. meters per second squared. So how do we find h of t? Okay, I know that a equals 9.8, okay, meters per second squared, and I know that a is the derivative of the velocity. So that means that dv dt equals 9.8, right? So what is v? That would be the integral of 9.8, right? It's an antiderivative of the acceleration. So the integral of 9.8. What is this? What's the integral of a constant? What's the integral of 2? 2x. So what's the integral of 9.8? 9.8t, because our variable now is time. So that's 9.8t plus c, remember. But now we're going to use our initial condition. We know that initially, because if we had an initial velocity, then you have to put here. If you don't drop, and if you throw, there has to be a v0, right? So this constant will actually be telling you what is your initial velocity. Okay? In fact, let's do it more generally. Let's say you throw with the velocity v0. And the reason why I'm doing this is because we're going to come up with a formula that you start in physics. If you are taking physics without calculus, there's a formula that shows up in there that describes the position function based on acceleration and initial velocity. Do you know the formula I'm talking about? We're going to derive it right now. We know calculus, so we can do it. Okay? In physics, when you do it without calculus, you have to memorize all of those formulas. But if you know calculus, you really just need to know this relationship between acceleration, velocity, and distance, and then you can derive all those formulas that you had to figure out before, that you had to memorize before. So that means then the v of 0 is your initial velocity. So actually that c is our initial velocity, because if I plug in 0, that's going to be equal to 9.8 times 0 plus c. But on the other hand, I know that's my initial velocity. So c is v0. So we can now update our velocity function, which is 9.8t plus whatever the initial velocity was. Do you understand this so far? Now remember, we want to find the height function. So what do we need to do? Well, velocity is the rate of change of the position function. Our position now is height. So this is the same thing as dh dt. Yes? Velocity is dh dt. So now, what is h? It will be the integral of this. Yes? The integral of the velocity function. So we just need to find an antiderivative. Now, the same way that derivative distributes over addition, integration will also distribute over addition, right? So if you want to find an antiderivative of x plus x squared, what do? Find an antiderivative of x, find an antiderivative of x squared, and then you add them. Because when you take derivative, you're going to get the original one, right? Because derivative distributes, so integral also distributes. I'm going to write all of these formulas properties right now. So the point is that now we can do this once again. What's an antiderivative of 9.8t? So 9.8 over 2t squared, which would be 4.9, right? And what's an antiderivative of v0? v0t. Remember, v0 is a constant. v0t plus an arbitrary constant. Now, what is this c responsible for? That's the initial height. Because when t is equal to 0, h equals c. So the constants here have a meaning. The first constant was initial velocity. The second constant that we're getting is the one telling you the initial height. Depending how high you are, of course, will be, the position formula. So using the fact that h of 0 equals h0 implies then that h of 0 is, okay, so 4.9 times 0 squared plus v0 times 0 plus c, and we know this is h0, so c is h0. So moral of the story, we get that the height function of an object when you throw it with an initial velocity v0, and the only thing that is acting upon it is gravity. Here we are neglecting a resistance and any other forces that could be slowing the object down. Okay, we're just free fall, like nothing else. We are ignoring everything else. Okay, that's your equation. This is one of the equations that you memorize in physics. maybe we're 16 here if you use feet per second instead of using meter per second squares. Instead of using meters, you use feet. I think it's a 16 here because I think the acceleration is 32, if I remember correctly, instead of 9.8 meter per second squared. So I just want to show you how important this is. This is actually what we use in real life. Okay, this is the kind of stuff that we do. Did you understand this? You have questions like this in the home. Okay, so now you don't need to memorize this formula anymore. And when I was in high school, I had to memorize this. And I had to work with this every time that I had a physics problem. Now you don't have to. You just need to remember acceleration, derivative of velocity, velocity, derivative of position. And then you integrate and you get what you need. Okay? All right. So you have seen already a couple of properties. So let me go ahead then and summarize those properties. Okay? So call those basic integration rules. Are there any questions? Do you understand that everything that I've explained? So what is it? Two different languages, but they are all the same. The integral version and the differential equation version, but they basically are asking you the same type of question. Okay? All right. So now let's focus on how do we find antiderivative. And the point is that derivative and integration, they are actually inverse of each other. Quotation mark. And I'll tell you why quotation mark. Okay? But in general, you can think of them as being inverse operations. So for example, let's see that remark. So let y equal f of x, capital F, be an antiderivative of little f. Okay? Then let's see what happens if I take. Let's see, inverse operation means that if I do the two operations one after the other, they should somehow cancel each other, right? Like you take square root and then you square, they cancel each other. That's what inverse operation means. So let's see, what I want to do first. Okay, so let's do first integral and then we do derivative. So I'm going to do the integral of f of x, and then I'm going to take the derivative of this. Okay? So I'm doing the integral and then I'm taking the derivative. And then let's do it to be truly an inverse relation, then we should do it the other way around as well. What if you take derivative first? Now, of course, then you need to change the input and output, and then we take integral. So let's see what we obtain, okay? All right, so if they are inverse operation truly, I should get as an answer here f, little f, right? Because they cancel each other. And if they are inverse operation truly, I should get as an answer here capital F. Everybody okay with this? So let's see. So let's calculate this. So what's the integral of little f? Big F plus c. So this is going to be the derivative of big F, which is an antiderivative, plus c, as you all know. All the solution to the integral is always like that. And what happens when I take derivative of this? This is going to be little f, because that's going to be capital F prime plus 0, right? Which is just little f. So, okay, if you do it in this way, the derivative cancels the integral. There's no question behind that. Does that make sense? If you integrate and then take derivative, they cancel each other, and you end up with the original function. How about the other way? What happens if you take derivative of capital F? What do we get? We get little f. So this is the integral of little f. So now, what's the integral of little f? Big F plus c. So that's the reason why I put inverse in quotation mark, because they are not technically really inverse functions, because when you do this direction, you don't really recover the original function f. You recover a version of it, a member of the family, right? Because there is this constant that pops up. That could be a 3, a 4. If it's a 0, okay, you have f, but it could be something else. Do you understand this? So they are not really inverse to each other, but to a sense, they behave like so. Because, for example, if you do integrate and then derivative, you do recover the original one. Here, you recover it up to a constant. So that's why we always have this plus c going around all the time. So this is very important, the plus c. Okay? That's very important. But then this tells us, because of this relationship, that actually, most, if not all properties, in fact, I dare to say all properties and formulas that you know on the derivative world, now they are going to have an integral counterpart. Okay? The product rule. The quotient rule, not really, because quotient rule is really just a combination. You can think of it as a combination of product rule with chain rule. Okay? But product rule is going to have a counterpart. Chain rule is going to have a counterpart. The power rule is going to have a counterpart. And all of those. Okay? All of those, the rules that we know for derivative, we're going to have something on the integral side. Now, we're not going to get to the product rule one. The product rule on derivative is called integration by parts. On the integral side, you're going to do that in Cal 2. In Cal 2, you're going to start integration by parts. Okay? But we are going to get to the chain rule. For example, the chain rule at the derivative level is what allows to do what we call the substitution technique on the integral level. Okay? So, but before I get to that one, that will be the next section that we're going to discuss, substitution. Let's talk about the basic ones. Okay? So now here I have a little, it's actually very long, but at this point you should know all of these things that is on this column. These are just all the formulas for the derivative of the functions, right? Sine, cosine, tangent, power functions, e to the x, ln, the rules of sum, addition, subtraction, constant multiple. You know all of these things for derivative, right? We have been doing this since the beginning. Each of these have a rule on the integral side, so that's what I'm gonna write right now, okay? So let's fill in what are the corresponding integration formulas that we obtain from this rule, and then we can add those formulas to our toolbox when we're solving integrals, when we're finding antiderivatives, okay? All right, so I'm gonna do those in blue. Let's see, we know the derivative of a constant is 0, yes? So what would that mean in terms of integral? Remember, if I'm gonna integrate both sides, then this tells me that the integral of 0, the integral cancels the derivative, so I'm going to get constant plus c. But what's a constant plus c? That's just another constant, so it's just, we call it c. Yeah, okay? So that means that if you integrate the 0 function, now we think of this as the 0 function, okay? Then what we get is just a constant. Does that make sense? And by the way, this actually tells you how you can check if your work is correct. Whenever you compute an antiderivative, whenever you do an integral, if you want to know if you did it correctly, take the derivative and you have to get the original function. If you don't get the original function, then you did something wrong. Because you see, when you take the derivative of your integral, you will get the original function. Okay? So, if you want to verify this, all you have to do is, okay, to verify this formula, just take the derivative of your result and make sure that you get the original one. Is it true that the derivative of c is 0? Yes, it is. So there's no discussion. Okay? So this is what we're going to do to be able to justify all the formulas. So the second one says that you can take constants out of a derivative. This translates into the fact that you can also take constants out of an integral. Okay? So the integral of a constant times a function equals the constant times the integral of the function. So you can take constants out. And again, you see, I'm just going to do it with this one. If you want to check this property, what do? Take the derivative of this. Okay? So if you take the derivative of this, what happens? K goes out because of that rule, and then you end up with the derivative of this integral. What is the derivative of this integral? What is the derivative of this integral? F. They cancel each other. We just said that. It's F. So you get K times F, which is exactly what we have. Okay? So that's how you can check if your formula works. Okay, so here this means the derivative of the sum is the sum of the derivative, same thing with the difference. Okay, the same idea we have it for integrals. So the integral of a sum
equals f.
is the sum of the integrals. So it's the integral of f of x. I should write smaller or have smaller arrows. Is the integral of f plus the integral of g. And if you have a difference, you also have a difference here. Okay? So, the integral distributes over addition and subtraction. All right. And again, just like in the case of derivative, we study a few basic derivative rules, and then this all of a sudden open the door to finding derivative of a bunch of functions, right? Same thing here. Yes.
So are both sides equal to each other?
Yes. Yes. Here I don't need to write plus c because the c on the left is already including the c on both left and right have an arbitrary constant. You see? When you say both sides, what do you mean? You mean here, right?
So, the differential and the integration formula, are they like equal to each other?
No, not equal. Like they correspond to each other. Like this formula leads to this formula, and if you want this formula, then I don't want to say this formula leads to this one because to make sense of this, you need to know about derivatives first, right? Because how do we define this? Antiderivative. If you don't have a notion of derivatives, you cannot make sense of this, right? It's just that this leads to this, okay? So the red, I'm giving you what that gives, the new knowledge that it gives you, which is the blue, okay? Which is what we're gonna use for our integration purposes. Okay, so this means that the derivative of a constant times x is just k, right? So that means that if I integrate a constant, what's the answer? What happens if you integrate a constant?
It's k times x.
It's k times x plus c. Remember, plus c. Okay? Remember, here the derivative, here, when you see this, you know that k is a constant because by this notation, I'm telling you that our variable is x. When I write dx here, I'm telling you our variable is x. Okay. All right. Now comes the power rule. So now, here we need to think about how do we reverse something like this. Okay. Now, here is a sort of thing. This rule is true for what n? This is true for all real numbers except a particular n. What is it? What's the only n that this rule does not apply for derivatives?
0.
No, 0 is okay because then you get 1, and then there is 1 is 0, and then 0 times that will be 0, so that's fine. There is a value of n that this rule does not apply. Which one is it? -1. If n is -1, what is this function? What is this function if n is -1? Okay, over x. What's the derivative of 1 over x? ln. Nothing to do with this. Do you understand this? So this rule is valid as long as this guy is not a -1, right? When this is a -1, we have a different rule, which is the natural log. Yes? So, as long as n is different than -1, now this is true for any real number, remember, even though you see n here, it is not limited to an integer. This applies to a 1/2, so if you have a square root of x and so on, you can use it, right? This is the power rule for derivatives. As long as n is different than -1, we have this condition. Then let's think about how can we undo this process, okay? And this is the one that leads to the following. In x to the n, the antiderivative of x to the n is x to the n plus 1 over n plus 1. So be careful because this is where students make mistakes sometimes. When you take derivative, you subtract 1 from the exponent. Now to compensate that subtracting, what you need to do, you add 1, right? This is so that they cancel each other out. If you subtract, you need to add to cancel that effect. So notice that if you take the derivative of this, what happens? Using that rule, this comes down, canceling this, that's why we need to divide by that, and then you subtract 1 and you get your x to the n. Everybody okay with this? Now, keep in mind that this is for n different than -1. Of course, this wouldn't even make sense if n is -1, because this wouldn't be defined, because this would be 0. Yes? But as long as n is different than -1, we have the power rule. You're going to be using this 1,000 times. Almost every integral involves a version of this. Okay? Or unless you're just doing sine or cosine. But power rule is used a lot. As you know, from the derivative, you use power rule a lot, right? When you take derivative. Same thing for integrals. Now, here is raise the power by 1 and divide by that power. Okay? So what's the integral of x cubed? X to the 4 over 4. What's the integral of x to the 20? Quickly.
X to the 22.
21. X to the 21 over 21. Right? It's easy. It is not hard. But remember, you need to add, you not subtract. Okay? Because you need to think backwards now. Okay. Now we come to the trigonometric part. By the way, with what we have here now, we can take the derivative of any polynomial, integral of any polynomial. Because if you combine the constant multiple together with the sum and together with the power rule, now you can take any polynomial. Because any polynomial, you break it up into little integrals, and each integral, they look like a constant times x to some power. Use the constant root to take the constant out, and x to some power. So now any polynomial that comes your way, you can find an antiderivative. Okay? We'll do examples. All right. So we know derivative of sine is cosine. What does that mean? If you integrate cosine, what do you get? Sine. So remember, just ask yourself, I need a function whose derivative is cosine. And hopefully the sine function will come to your mind. Okay? It's not negative sine, it's sine. Now we know that the derivative of cosine is negative sine. So what does that mean about the integral of sine?
It's cosine plus c.
Negative cosine. You remember, if you say cosine, what's the derivative of cosine? Negative sine, but we want sine. So we need to put a negative to get rid of that, right? To cancel the negative the derivative gives you. So it's negative cosine. You okay with this? So I don't know if this may be helpful or not, but I guess I'll show it to you. There is this little picture that you can think about to have that clear. So you do, like a little circle thing if you want, and then up here you put sine, here you put cosine, then negative sine, then negative cosine. Okay? So if you move clockwise, you're doing derivative. So when you move like this, what you're doing is derivative. Okay? If you move like this, you're doing derivative. For example, derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, and so on. Okay? Now, if you move counterclockwise, you're doing integration. So if you move like this, you're doing integral. Okay? So the integral of sine is negative cosine. The integral of cosine is sine, and so on. Okay? So if you find yourself having trouble remembering this formula for sine and cosine for the integral, just think about this picture and understand that you should realize that clockwise is derivative, because when you move clockwise, sine gives you cosine, and cosine gives you negative sine. So that tells you that you're doing derivative. And if you do it the opposite way, which is counterclockwise, then you're doing integration. Okay? So you want to know what the integral of cosine is sine. You want to know what the integral of sine? Negative cosine. Okay? This is just a way to remember these things. Just like the SOHCAHTOA thing that you have for trigonometry and all of that things. Okay? All right. Just a nice little pattern that is in there. Okay. How about this one? So we have the derivative of tangent secant squared. So, what's the integral of secant squared? Tangent. Do you understand this? All right. How about this one? So derivative of secant is secant tangent. So that means if you have the integral of secant times tangent, that's just secant plus c, remember? And then this one tells us that integral of cosecant squared, this is negative cotangent. Why negative cotangent? Because we need to compensate this negative. Okay? I'm just doing things. Then integral of cosecant times cotangent is negative cosecant, because we need to compensate by the negative. Now, derivative of e to the x is e to the x. So what's the integral of e to the x? E to the x. Now remember, plus c, okay? It comes back with an arbitrary constant added to it. All right, almost done. Then similarly, we have this one. So let's see. Who can tell me this formula? What do you think this should be? This is now an arbitrary exponential. As you know, e to the x is itself. But when you have an arbitrary base, it's going to be itself plus natural log of the base. Times natural log of the base, right? We have that extra thing in there when the base is not e. So what will be the corresponding integral formula? Now, for example, you're going to integrate 2 to the x, right? That will be the formula corresponding to this case. How do you do it? So what will be the formula? Just think about what will cancel out this effect. Divided by that, right? Remember, you want to cancel stuff. So what will cancel the product effect of the derivative? Dividing by that. Yes? So this is going to be a to the x over ln of a. So what's the integral of 2 to the x? 2 to the x divided by ln of 2. Does that make sense? Okay. Now here, this second, so this one, you know, the derivative of the natural log is 1 over x, right? But that's for x greater than 0. Now it turns out that if instead of natural log, you look at natural log of absolute value of x, this is in a sense is a better function than this one. Why is this better? Because the domain here is bigger. Now here, the domain here is the only restriction is that x has to be different than 0. All of a sudden, we open ourselves the entire real line, and we're just skipping 0. Okay? So this function is better than the previous one, and it turns out that they both have the same derivative. Okay? The derivative of ln of absolute value is equal to 1 over x. To do this, you need to write as a piecewise. When x is positive, you have this formula. When x is negative, you're going to have ln of negative x. Using chain rule, you're going to have negative 1 over negative x, which again give you 1 over x. Okay? For the negative version. The point is that the derivative of ln of absolute value is the same thing as the derivative of just ln. It's 1 over x without absolute value. Okay? So, because this function is better, this is the one that we're going to take for our antiderivatives. Okay? So when you take the derivative of 1 over x, and the integral of 1 over x, when you integrate that, the antiderivative that we're going to pick is this one because this is a better function than the other. Okay? So, integral of 1 over x is not natural log of x, it's natural log of absolute value of x. We're going to take the best antiderivative. Okay? Which is this one. Okay. So, I guess you just need to remember that. Okay? That's something you need to remember. You put absolute value. Now we come to the inverse trig function. We know the derivative of inverse tangent is 1 over 1 plus x squared. So that means that if you come across the integral of 1 plus x squared, this is going to be inverse tangent. You're going to explore these guys in Calc 2. Okay, at the beginning of Calc 2, you're going to start doing integrals, exploring these formulas. Okay, because this formula is the basics for example, if you want to do this, integral, you do some algebra and some manipulations, but at the end of the day, this is going to be a version of the inverse tangent integral. Okay, but because there are some constants in there, we need to do some work. Okay, but if we have, I don't think we have time to show you that this semester, but in Calc 2, you're going to start doing that kind of stuff. That's what you're going to do most likely at the very beginning. Okay, and then similarly here, this means that the integral of 1 over square root of 1 minus x squared, then this is the arcsine function, so as the inverse sine. And then this one, now what we do is, because the derivative of the inverse secant of absolute value of x equals to this, and if you remember, when there is also another formula which is inverse secant of x, and then the absolute value transfer from here to here, we can do that. So that means that when you integrate this, we're going to get, when you integrate this, normally you have this absolute value here for the derivative formula, but you can transfer that to here. So an antiderivative of this function is this one with the absolute value over here. Okay? So this is the formula. This is the inverse secant of absolute value of x plus 0. Again, notice that all of these formulas, we got them for free. Okay? You know the red formulas, we are just doing them backwards now, and we're getting the blue ones for free. Okay? Now, you just need to practice to get used to the new formula. You're used to the derivative formula. You're used to bring stuff down and subtract 1. Now, you need to get used to add 1 and divide by what you by the power that you have. You need to get used to that. The only way to do that is by doing products. Okay? That's how you can get used to it. So,
I don't understand the first one, like the constant. I don't understand the 0, like.
0 is a function. So the question is, what's an antiderivative of the 0 function?
Okay, yes, now I understand. So I was writing when you were saying all that. And then...
Remember, that symbol is a statement. What statement is that symbol? an antiderivative of whatever function is whatever you're saying is equal to. So here we're saying an antiderivative of the zero function is a constant function. In fact, all antiderivative of the zero function is any constant. That's what we're saying in that line. Okay? Remember, this is a language. Okay, are you okay with these basic rules? So now, of course, let's do examples. Let's put this into practice. So, samples, and here we just need to do a bunch, okay, to see. So, evaluate. And then, let's see. Integral of 3x dx. Integral of 1 over x cubed dx. Integral square root. Okay, so let's see. Let's do all of this together, and then I'm gonna give you others for you to think about while I take attendance, and then come back, etc. Okay, so let's see. How do we do something like this? Let's see. The first one I'm gonna do it formally with the properties, but then the others are not gonna be as formal. Okay. So basically, for the first one, what can we do? We can use the constant multiple, meaning whenever you have a constant multiplying your function, just make your life easy. Take it out. Okay. Same thing that we do with derivative. You take the constant out, and then you worry about the function. You don't do product rule. If you have 2 times x and you want to take the derivative, you don't do a product rule. You're cool, but you don't do it, right? This is 2 times whatever the derivative of x is, which is 1, and you're done, right? Well, same thing for the integral. So 3 times x, okay, this is 3 times whatever the integral of x is. That's a constant multiple rule. And now, what's an antiderivative for x? Power rule. That's x to the 1. So we do x to the 1 plus 1 over 1 plus 1. So let's blindly use the rules, okay? So this x to the 1, right? X to the 1, just to make it explicit. So this is 1 plus 1 over 1 plus 1. That's where the x squared over 2 is coming from that we have been talking about since the beginning today. Okay? So we see that this is just 3/2 x squared plus c. Do you understand this? Okay. How about the next one? Now, just as in the derivative case, sometimes it helps to rewrite your function before you start, computing. In this case, we know that if you have, remember, for derivative, what was the goal? If you have x to some power, it's very easy to take derivative, right? Use power rule. Well, same thing here. If you have x to some power, it's easy to integrate. Use the power rule. So can we write 1 over x cubed as x to some power? X to a negative 3. So we can write this as x to a negative 3. Yes? Now, use power rule. So what is this? X to a negative 3 plus 1 over negative 3 plus 1. And don't forget the plus. In other words, this is going to be negative 1 over 2, and then there will be x to a negative 2. I'm going to write it as x squared in the bottom. So negative 1 over 2x squared. Are you okay? Do you understand why there is an x squared in the denominator? This is a negative 3 plus 1, the x to a negative 2 that we have on top. Okay. Similarly, if we want to do the integral of square root, how do we do this?
X to the 1/2.
So we write as x to the 1/2. And now activate the process. So this will be x to the 1/2 plus 1 over 1/2 plus 1. Remember, you need to add, don't subtract. You're used to subtract. Now you need to add stuff. Okay? That's why you need the practice, so you get used to it. So it will be x to the 3/2 over 3/2. And instead of writing this, typically we write 2/3 x to the 3/2. Questions? Okay. Now, how about this one? You see, let's do this one in one shot. This is 2 times sine. So again, constant multiple, so the 2 stays there, right? Now we just need to find the antiderivative of sine. What's an antiderivative of sine? negative cosine. Okay, so the answer here is negative 2 cosine of x. And then, of course, when it's something simple like this, just check your work. This is your answer. Take the visually take the derivative. Make sure that you get this. What happens if you take the derivative of this? You get negative 2 times negative sine. The negative cancel, you get 2 sine, which is exactly what you started with. You're good to go. Here, you take the derivative of this guy. What do you get? 3 half comes down, cancel the 2/3, and you get 3 half minus 1. That's a 1 half. X to a 1 half. That's what you started with. So you're good to go. Okay? So when it's simple like this, it's very easy to check your work. Now, if you get a huge thing, you can check, but then you will spend some time trying to take the derivative. At that point, you should trust your work. But when it's stuff simple like this, just check. All right. So let me give you some more. Now, slightly more interesting. So how about x squared plus 1? Then do, as I said, any polynomial now that comes your way is yours for the take. Can do it. Now let's make it slightly more interesting. And then even more interesting. Okay, so here you have 4. Go for it. You take attendance. Let's see, number 5. What is this?
X cubed over 3 plus x plus c.
Very good. So you understand this? Right? Okay. Next one. Yes?
Is 3 over 4. No, wait, 3x over 4. 3x5 over 4. 5.
Over 5. So you divide by whatever power you have. When you use the rule, whatever new power you obtain, you divide by that. Okay, so let's see. 3x to the 5 over 5. Yes?
Minus 5 cubed over 3.
Good.
Plus c. No, wait, 1.
You are taking, so I'm glad that you're doing this because sometimes this happens. You will take derivative instead of taking integral. You are integrating, you're not taking derivative. What's the integral of x? The same thing that you have been doing.
1 over 2, basically.
X squared. The power rule, the same thing you have been doing. X2 over 2. No, I mean, it's good that it happens now. I mean, it's not good that it happens on Wednesday, right? Or on the homework. Well, on the homework is okay. On the quiz, it's not good, right? So you need to keep in mind that you're now taking integral, not derivatives. Okay, so be careful. The only way to get used to it is what?
Practice.
Practice. You just need to sit down and do problems. Okay. How did you master? Did you master factoring?
No.
Why?
I didn't.
Because you didn't sit down and do problems. That's the only thing that you can master something if you just do it. Do you think you can be a good chef or a good cooker if you don't just try cooking stuff at home? You need to cook. Just by looking your mom or somebody else cook is not enough. You have to do it. So looking at me is not enough. When I do stuff, you may be like, oh yeah, makes sense. Yeah, I understand. But then and when it's your turn, it's a different story. So you need to do it. Okay?
I keep stumbling because I keep forgetting the numbers.
Yeah. So typically, because this is a polynomial, we typically like to write as coefficients times x to something and so on. But if you leave it as the one on top, that's fine. Okay. So 5 and 6, no problem. How about 7? If I ask you to take the derivative of this, what would you do? Robert, what would you do?
I would convert the bottom radical into a -1/2 and do product rule.
Yes, but what else can you do?
Split it up.
Why do you guys like complicated stuff?
X
Split,
over root.
simplify, and it's just 2 power rules. split, simplify, and then you just need to do 2 power rules. Yes? Or if you write as x to the 1/2 to the negative 1/2, distribute it. And then you have 2 power rules. Why take the difficult way? There is a very easy way in front of you. And basically right now, that's the only thing that we can do because we don't know how to deal with fractions when it comes to an integral. For derivative, yes, you have the quotient rule, or you could do a product rule if you wanted, like bring it to the top. But here we only have basic stuff. So what can we do? Split, use power. Okay? So remember these things. So here the idea is, okay, you can split. And then simplify. The first one is square root of x, right? Or x to the 1/2. And the other one is x to the negative 1/2. Don't forget the dx. Remember, every time that you write this symbol, it comes attached to the dx. You don't write the dx, I don't know what you mean. I mean, I know what you mean, but you're misspelling something. Okay? So those two things, they come together. Do you understand this so far? So again, split these 2 fractions. This is x to the 1 over x to the 1/2. 1 minus 1/2 is 1/2. Okay? And this one is x to the 1/2, bring it to the top of negative 1/2. Yes? Why did I do this? Because now we are in a position that we can use power rule for both. Alright? So let's do it. Which, by the way, if what you wanted to do is derivative, this is what I will do. I will write it like that, and now I will take derivative. Because now it's pretty easy to take the derivative. Okay? Alright, so now let's integrate. So what do we get? What's the first integral?
2 over 3 plus x.
Let's see, let's do it a little bit more slower. So x to the 3/2 over 3/2, right? And then plus, what's the next one? X to what power?
X to the 1/2.
X to the 1/2 over 1/2. Remember, you need to do plus 1. So negative 1/2 plus 1 is positive 1/2. Okay? So what's the final answer? 2/3 x to the 3/2 plus 2 times square root of x. Or you can write x to the 1/2. Whatever you want. All right. Questions? Are you understanding what's going on so far? Okay, now, just like in number 7, we needed to do some small clever manipulation, if you will, before we actually got to integrate. In number 8, we have to do something slightly more clever, okay? Why? Because there is no splitting here. Right? If you were to be the other way around, then yes, you can nicely split and then do the same technique. So, what do we do in this case? In general, we're not going to discuss rational functions in general. That's something that you're going to do in calculus 2. There is a general technique called partial fraction decomposition that you probably learned back in pre-calculus, which allows you to write a fraction as a sum of little fractions that have a specific form. And each of those little fractions are going to be easy to do the integral. So you're going to do that in Cal 2. And now there are some cases that you can easily solve them, like in this case. Now, I'm going to do a quick way, and then I'll tell you in general what you can do when the degree of the top. Later, once we talk about substitution, we're going to talk about what to do when the degrees are the same, like in this case. The degree of the top and bottom are the same. What you do is long division. You divide. Okay? But right now, there is a trick that I will do. I just want to show you this for you to know that you can do this kind of stuff if it works. So remember, the good thing about math is that when you're doing a problem, you try something. If it doesn't work, erase and try something else. So throw the paper out and start anew. Okay? So you just want to do something that's valid algebraically. So you don't want to force stuff, right? Please, hopefully at this point, nobody's thinking about doing this kind of stuff. Okay? Please. Because I saw this at the beginning of the semester. So don't do that, okay? So as long as you do things that are algebraically valid, then you're good to go. And, we have rules. Those are the ones that we can use. So I'm going to do something here that probably you wouldn't think about it, but now once I show it to you, that's another technique that you can incorporate to your tricks, if you will. I'm going to add and subtract 1. Why am I going to do this? Because by adding and subtracting 1, then all of a sudden, I'm going to have x squared plus 1 minus 1. I can split. That squared plus 1 cancel with this, give me a 1. I know how to deal with that. And then the other expression that I have is a 1 over 1 plus x squared. And we know what is that. That's inverse tangent when you take the antiderivative. Okay? So, again, this is just to show you that you can add and subtract stuff. Whether that will help you or not is a different story. But keep in mind that sometimes that's all you will need to do. So, what I'm going to do is, I'm going to add 1 and subtract 1. In general, really what's going on is talking about if you do long division. Okay, if you divide this by this guy and you write as quotient plus remainder of the divisor, you will end up with the simplified version that I'm going to obtain. So the reason why I did that is because it will allow me now to split okay, and therefore we're going to obtain this 1 minus 1 over 1 plus x squared. Let me write it like that so it looks more familiar. And now we can integrate this. By the way, if you do long division, this is what you get. This will be your quotient with remainder -1. Okay? That's what you get. So now integrate. So what's the integral of 1? X. And what's the integral of x minus? What's the integral of 1 over 1 plus x squared? What function you know whose derivative is 1 over 1 plus x squared? Inverse tangent. Remember, if you freeze out and you don't remember the formula, ask yourself that question. I need a function whose derivative is that. And hopefully the inverse tangent will come to your mind. Okay? All right. Questions? Okay. For example, let's see, use this, practice the same technique with this one now. Term, what do you get? You can do it. Even though it's not straight from the formulas, you can do it. So let's see, when you see something like this, why would you think about that kind of trick? Well, ask yourself, okay, if, first of all, I don't know how to do this right away because of the t. So if I didn't have the t, do you know how to do it? So let's put a 1 here instead of a t. Do you know how to do it if you had a 1 in here? Imagine for a second, if you had a 1 here, what would be the answer? Because if you can do that, then you just do the trick so that you can get the 1 to show up in here. That's what I did in there. If I had a 1 in there, do I know how to do it? Yes, that will be inverse tangent. Okay, what trick can I do to get a 1 to show up in there? Adding or subtracting and split. Okay, because then you will have nice cancellations. So let's play this game. If you have a 1 here, what do you think will be the answer? Think about a function whose derivative is 1 over t plus 1. What function is this? Problem solving. You need a function whose derivative is 1 over something. What comes to your mind when I say this kind of stuff? ln is better because there is no square root here involved, right? So when you do the derivative of ln, it's 1 over the argument, right? Now, there's a little chain rule involved. Now, question, ln of what will give you 1 over t plus 1 as a derivative? ln of t plus 1. You understand this? So if that was a 1, you know how to do it. So now, do the trick to make the 1 show up, and now you get your answer. So remember, the reason why you take so much math courses is so that you can learn how to solve problems. It's not, you're not going to be walking around solving integrals for people. The computers do this for you. But you need to bring certain level of intellect and problem solving skills to the table when you go somewhere. That's why you take math. Because it's one of the things that really allows you to get your hand dirty in solving problems and thinking and trying to find solutions where it looks impossible, but then you find a way to go through. Okay? That's the value in doing these things. Unfortunately, most of the time you guys neglect the math studies and then focus on other stuff. That many other courses is just memorizing things and memorize and memorize and memorize. Memory can only get you so far, okay? But the reasoning, it goes with you forever. 3 years from now, I probably ask you something from biology and you're not gonna remember. But you know, if you learn how to reason, then that goes for you for life. That's what I'm trying to convey to you in one way or another, and what we try to do with math. Okay. Anyways, so what will be the answer? What did you get?
T minus n, t plus 1.
Very good. Now, what's the catch? Absolute value. Remember, every time that we use ln, we want to put the absolute value. We take the better antiderivative. Okay, the absolute value. Good. So again, here the trick is that we're gonna add 1, subtract 1, because I want to get that 1 over t plus 1 to show up. And when you split and simplify, you get this. Everybody okay so far? And now, integral of 1, okay, that's t. Remember, our variable is t now. And then integral of 1 over t plus 1, that's ln. And remember, we have this little thing that if you stick the absolute value, it still works as an antiderivative, and this is a better function because now the domain is everything except -1. If you don't put absolute value, the domain is only greater than -1. So that's some restriction. Okay. Now, if you're doing an actual problem and you know that your variable is going to satisfy the restriction, it's okay to get rid of the absolute value. But in general, we put the absolute value. Okay. Questions? All right. So I guess let me just, I mean, we could be doing more exam. I guess let me show you one more. And now the rest is just the same thing. If we wanted to do the cube root of x times x minus 4. Who can tell me how would you attack this problem? What would you do to solve this problem?
First, I'm trying to figure out the 3 cube.
Simplify, distribute.
So you write as x to the 1/3, distribute, and you're gonna have 2 power things. The point is that this reduced just a power rule problem. Okay? So remember, try to have a plan. Maybe the way it is not clear what to do. But if you write this as x to the 1/3 and distribute, you're gonna have power stuff, and then you can use the rules that we have been using, the power rule. Okay? So just keep that in mind. So write it as x to the 1/3. Distribute. Remember, when you distribute, you need to add the power. So 1 plus 1/3. What is that? That's a 4/3. X to the 4/3 minus x to the 1/3. And now we integrate. So what's the first integral? You add 1, so that would be 7/3. 7/3 minus 4 times add 1, so that's 4/3 over 4/3 plus c, and now simplify. So the 4 here cancels with this one, so we end up with 3/7 x to the 7/3 minus, now the 1/3 in the bottom goes the way to the top as a 3, x to the 4/3 plus c. And this is typical. When you're doing this kind of integrals that radicals show up, then you're going to have a bunch of weird fractions popping up. So just make sure that you're comfortable with this, okay? And adding 1 to fractions, because every time that a radical shows up, you may need to do something like this. I wouldn't call this difficult, but you have to be careful because there are many places here where you could make mistakes if you're not careful. So how can you avoid that? By practicing. just do problems. Just sit. Starting today, just sit down and do 5 or 10 integrals. Just do 5, 10 integrals. Tomorrow, do 5, 10 integrals, and so on. Just randomly go to the book, the section. Probably you will even have opened the book that we have for the class. Just go there. Go to a section about indefinite integrals. There is a problem section. Just pick 5 problems. Do them. You are drinking your milk or whatever you drink for breakfast, and do 5 integrals, and then move on with your life. Then you do the homework and whatever you need to do. But this way, you know, you will get the hang of this. And you need to get the hang of this quickly. That's the point, because we have an exam a week from today. Okay? So there's nothing else that you can do. So that's what I'm trying to tell you. Just do problems. It doesn't have to be 24 hours a day. It doesn't have to be 10 hours a day. But just do it on a consistent basis. If you don't do anything and just say, okay, on Tuesday I'm going to sit down and spend the whole day, you're not going to solve anything by doing that. Okay? It's going to help you a bit, but it's not going to, it's better to just do a little bit every day. If you do something today, you get stuck, that's okay. You have to, the entire day, your brain is going to be working in the background. What was happening? What was happening? Tomorrow, when you look at the problem, you're going to look at it from a different point of view. But sometimes you need time for the ideas to sink in and process that. Okay? So trying to squeeze everything one day, that's not good. Yeah, we all do that. I mean, I understand. I used to do it also, but I recognize it's not good. It's not a good idea. And okay. Anyways, are you okay with this so far? Now let me show you that. So far the problems that I've given you, of course, the basic rules have applied kind of directly, but there are situations that we cannot just get out of very easily. For example, how about something like this? How about the integral of x squared times the square root of x cubed minus 1? How about something like this? You see, if the radical, so to speak, was here, then we could do it because then you could distribute and whatever. But the point is that here you cannot distribute, right? There's no way. You can get this guy inside as an x to the 4, but then you have a square root of something massive inside. How do you do that? I haven't talked about this. Okay? So the basic rules that we have so far will not get you to here. You will not be able to do this with the basic rules. So we need to do something more. Okay? And what's the idea? How do we do this? Well, there is another technique which is called integration by substitution. Okay? And you get that by exploiting the chain rule on the derivative side. We have the chain rule on the derivative side, then we have substitution technique on the integral side. I guess let me show you how we do this, and then if we don't have the time, then on Friday I will explain this more formally. But basically, the trick here is that when I look at this function, I see an expression, so that when you take the derivative, some or all or some of it is in there. When I say this is, if you're off by a constant, that's fine. Being off by a constant is not a problem because you can always multiply a constant, multiply and divide, and then you're good to go. Okay? For example, here I see x cubed minus 1. What's the derivative of x cubed minus 1? 3x squared. Do you see a 3x squared somewhere else here? I don't, but I see an x squared. That's good enough for me because you don't have the 3, but I can do it. I can put a 3 here and then divide. Yes? I didn't change the integral, and now we have the 3 squared. The point is, if you're off by a factor, by a constant, that's fine. If you're off by a variable, that's not fine. Because you cannot put an x here and then divide by x outside. You cannot do that. You cannot take variables out of the integral. But constants you can, okay? So if you're off by a constant, you can still do it. So I'm going to show you how this will go, okay? And then we're going to streamline this process, but just so you see a complete example. If I want to do something like this, the usual things are not going to work. So what I'm going to do is a substitution, okay? So a substitution is just a way of changing this integral into another one that then we can solve, okay? And what is the idea? My substitution, now the thing is you need to know what should be your substitution. What should you let, usually we call it U substitution. What should you let U be equal to? I'm going to let it be equal to this guy. Again, you get this from experience. And how do you get experience? Practice. Practice. Okay. But the question that you ask yourself is, what do I see here whose derivative is also there? Or some of it. If you're off by a constant, it's okay. And the only thing that comes to my mind is x cubed. But now x cubed minus 1. Always try to make it as complete as you can. Okay? So x cubed minus 1, the derivative is 3x squared. I see an x squared here. That's good enough for me. Okay? So what I'm going to do is I'm going to let u be equal to x cubed minus 1. So that means that the derivative of u du dx with respect of x is going to be 3x squared. Now, typically, in here, what we do is, because these are quantities by themselves, even though we haven't talked about it, you can manipulate these as quantities So we think of it as a differential. So we move the dx over here, multiply. So instead of writing du dx, what we typically say is, instead of this, we just say du is 3x squared dx. You can just think of it as moving this guy over here. So when you say u is equal to something, then du is the derivative of this times dx. Okay? It's just the dx that was here, just move it to the other side. Okay? Now, I want to do a substitution. Let's see. So far, remember, the integral is this one. So far, if thinking plainly about substitution, this is what I have. This part, I already have a substitution for it. I can write it as square root of u, so far. Yes? Because this is, I'm calling this u, so far I can write this as square root of u. Now I have to do something about this x squared and this dx, right? First of all, because I'm changing from x to u, now I need to have a du, I cannot have a dx, okay? That's okay, the du is coming in here, okay? And now if I put this du here, that's not good because du is equal to 3x squared dx. Now I have x squared dx only here. Well, that's fine, divide by 3, right? So this means that du divided by 3, you can manipulate this as a regular equation, is x squared times dx. Why did I do this? Because here is x squared times dx. So that x squared dx, how else can we write this when we do a substitution?
du over 2.
Du over 2. So let me rewrite this. So now, this 1 over 3 is just a constant, right? So we can take it out. So this is 1 over 3, the integral of square root of u du. So we change this original integral for this one. So now the question is, this only will work for you if you know how to solve this one. Now, do you know how to solve this integral? Yes, we just did that. This is just square root. So now we solve that one. So as you know, we write it as u to the 1/2. Use our power rule. So it will be 3/2 over 3/2. So we get 2 over 9 u to the 3/2 plus c. But then of course, the original variable is x, so we need to put the final answer in terms of the variable x. So now we just put back whatever u was equal to. So what was u equal to? X cubed minus 1. So this is 2 over 9 x cubed minus 1 to the 3/2 plus c. And you can check. If you take the derivative of this, what do you get? What happens if you take the derivative of this? Let's see, let's check. So to check, we need to take the derivative of that expression. Right? So the c, you know, doesn't count. So then what do we get? 2 over 9 power root times 3/2 times x cubed minus 1. 3/2 minus 1 is 1/2, right? And times chain rule. The derivative of the inside, which is 3x squared. Many of you were forgetting the chain rule in the exam. I started grading the exam, and many of you are getting questions wrong because you didn't use chain rule. Okay? All right. So simplify. So the 2 cancel with the 2. 3 times 3 is a 9. Cancel with this 9. What do we end up with? X squared times square root of x cubed minus 1. Exactly the original one. Okay? So what I just did is what we call technique by substitution. And basically what we are doing is we're undoing this chain rule process. Okay? So I'm going to, on Friday, I'm going to formalize this, write down the statement about the substitution technique, but this is basically what's going to be happening. Okay?